Hello everyone and welcome back. So what we're going to start off with in chapter 5 is talking about permutations. And this is a little bit different from what you're used to hearing about permutations, which is, the number of ways to arrange things, but it is a related concept. So we will be talking about things that are like that. Essentially, this is, in some ways, an arrangement of things, but we're talking about it in a little bit different terms. So first off, let's talk about the definitions here. A permutation of a set, oops, that is too small, hang on. I guess you can probably guess what I was doing to have it that small. A permutation is essentially a function from the set to itself that is both one-to-one, one-to-one and onto. In other words, it maps everything in the set to an element in the set, and it never maps anything to two elements, and it always, everything gets mapped to. I'll draw a little diagram below to show you an example, but then we'll start talking about this in some sort of formal symbols that will make it a little bit easier to deal with. And we'll go through several of those over the course of the chapter. Now, a permutation group, as you might imagine, is related to a set of permutations, because groups are always sets. But here, permutation group of a set A is a set of permutations that forms a group under function composition. So in other words, we're thinking of permutations themselves as functions, and if we use our operation, our binary operation as function composition, if that makes the permutations we have form a group, that is what we call a permutation group. Now, one thing that I do want to mention here, this is a set of permutations. A permutation group doesn't necessarily have to be all permutations. A lot of permutation groups that we will be talking about will include all possible permutations, but in order for it to be a permutation group, it doesn't necessarily have to include all possible permutations. So there are some examples where you might have some permutations in the group and not others. Now, if that's true, you do have to still make sure that the group is closed under function composition, because otherwise it wouldn't be a group, right? You can't take two of the permutations, compose them, and get something that's not in the set, then it wouldn't be a group. So it doesn't necessarily have to include all permutations, but sometimes it does. Okay, so that's what we mean by a permutation. So let's start off by looking at this as just a little diagram, and let's do something simple here. Actually, hang on. Let's do it this way. This thing will make circles for me. Why don't I just let it do the work? Black and, oops, circle. Okay. There we go. That's one, and here will be the second one. There we go. And oops. Let's move that up just a bit. There we go. That seems good enough. All right. So let's say we have let's say we have 4 elements in this first set. So let's call them A, B, C, and D. And so this is our set A, right? This is our set A. And this permutation has to take a set to itself, so this also has to be A. And let's put these same things over here. A, B, C, and D. Come on. C and D. Okay, so there is our set drawn out twice. And let's make these a little bit bigger just so we got them. And let's draw in some arrows. So let's say, for instance, B goes to A, D goes to itself, C, hang on, let me see if I can do this a little bit better. Let's say A goes to B. No, let's try making A go to C. This is going to be a little bit tricky. Okay, A goes to C, and C goes to A. Oh no, can't do that. Hang on. Already used A. So C goes to B. Okay, so here everything has exactly one output. Every input has exactly one output. Every output's hit. We never have anything mapped to two different things, so this is both one-to-one and onto. So that makes it a permutation. And onto. Okay, so this is a permutation. Permutation, check. So this, again, is a little bit different than what we're thinking about with permutations before, but in that we're not counting the number of ways you can arrange things, but it is still sort of an arrangement. If you look at what we have to start with, A, B, C, and D, and look at what we wind up with, what we're doing here is we're rearranging the elements. If we think of their natural ordering as A, B, C, and D, so let me just, if we think of their natural ordering, and we'll do this a little bit more precisely here in a second, in a way where the natural ordering is an actual natural ordering. But if we think of their natural ordering as A, B, C, and D, then what we see in this permutation is A goes to C, and I'll explain what this symbol means here in a second. B goes to A. Sorry, I forgot what I had go to what, but here C goes to B and D goes to itself. Oops. B, D goes to itself. All right, and let's fix this up a little bit. There we go. Okay, so in other words, you can think of this as a permutation. This is a reordering of what we have, reordering it from ABCD to CABD. So that's how it relates to what we're used to thinking of as a permutation. Now, this notation is a common one to show how a permutation works. So this is a common notation. To show how a permutation works. And here when I say a permutation, I mean a specific one. And we will, like I said, have other notations that we're going to use in later sections, some of which are going to be things that we're going to more commonly use, but this one is sort of a basic one. Now, what I would like for you all to try and answer here, I'm going to put up a question here. Bold question. Okay, done. Let's move that. There we go, and let's do one not in bold now. What permutation groups have we already seen? So what I mean by this is, remember, a permutation is a rearrangement of elements or mapping one element to another. And the operation that we have to use is function composition. What have we seen that's been like that so far? So think about that, try and answer it, and then unpause the video when you have. Okay, well, we do have a good answer for this here. And maybe you figured it out. Hang on. Answer. Oops. The group of symmetries of a square or a triangle, etc. Okay, done. All right. Hang on. So that is an example of a permutation group. Oops. That's an example of a permutation group we've already seen. So the symmetries of a square, think about it here. You had 4 corners. We even colored them. And what our rotations and flips did was moved them from one to another. In other words, the upper left-hand corner, which might start out as pink, would, under the function, become yellow. So your input was pink and your output was yellow. And the way we did this, we never had 2 of the same color on the final square, and every color was represented, so it had to be 1-to-1 and onto. Now, not, as we saw back in the video where we talked about that, not all possible rearrangements of those colors happened under this group, so it wasn't a group of all possible permutations, but it was a set of permutations that formed a group under function composition. So that is an example here. So this was D3, D4, D4, etc. We only looked at D3 and D4. D3 was in some questions in the homework and one little question on the test, and D4 was the one we did the video on in chapter 1. But there are ones for, it's not just for triangles and squares. You can have one for a pentagon, a hexagon, and so forth. So those are some examples. Now, how do we represent represent, and I've already showed you this, but I'm going to show how it works. How do we represent permutations? You can probably even hear me tapping on the screen, I don't know. How do we represent permutations and use this representation to compose them? And here I'm using the word compose. That's essentially function composition. It's just the verb version of it. So how do we use this to compose them? Okay, so that is our question here. Now, how we do it is we use this little notation that we have up here that I drew here. We call this array notation. And I'm going to put it in as a type of notation because we will have others, or well, at least one other. So we're going to start off with what we call array notation. And let's move it down there. There we go. Array notation. Now we will have something else. The next notation we're going to talk about is what we call cycle notation. But let's take a look at how array notation works. And for simplicity, we're just going to have our set be it doesn't have to be this, but for simplicity, we'll use a set of positive integers. We'll use a set of the first n positive integers. And here I'm going to use a specific n, but any n would work. And you'll notice I'm only talking about finite sets here. That doesn't mean you can't have permutation groups on infinite sets, or permutations on infinite sets. You can, and you can even have permutation groups, but we're only going to be looking at finite groups, first n integers. So let's pick out a number of integers here. Since we had 4 letters above, I'm going to use 4 numbers here. So I'm going to say my set A is 1, 2, 3, 4. And like I said, we're almost always going to use 1, 2, and so on up to whatever n we want here. So in this case, it's going to be 1, 2, 3, 4, but our set could be 1 up through n minus, or 1 up through n. So we could have a set like that. That would work just as well. But here we're just going to use 1, 2, 3, and 4. And I think what I will do is start out by showing you how they work. If I have time, maybe write them all. Let's see, 4. That would be 24. Now I'll use this as to show how they work. Then I'll write out all of them for a set of 3 integers. So 1, 2. We always write at the top. We write them in order. 1, 2, 3, and 4. That's another reason why we use the first n integers here. Hang on. I'll make that a little bit further away. That's another reason we use the first n integers, because there's a natural ordering there. And so, for instance, I might have 2, 1, 3, 4. How this works is the top row is the input, and the bottom row is the output. In other words, the things on the top row map to the things directly below them on the bottom row. So let me show you here what I mean. So here, let's put this in blue, I guess. 1 maps to 2, 2 maps to 1, 3 maps to itself, 4 maps to itself. So if you wanted to write this as a function, like say we wanted to call, if we call this permutation alpha, usually we use lowercase Greek letters to represent permutations. The laughing is my kid. She is laughing at some sort of anime or something. Maybe she's laughing at a video I sent her. I sent her one about Skyrim, where this guy was picking a lock, and it was called Heart Attack Level 100, and it shows him, it's mostly he's picking this little lock, and then when he gets done, this giant saber-toothed tiger attacks him. But she thought that was funny. All right, so if we call this permutation alpha, we would find we'd have alpha of 1 is 2, alpha of 2 is 1, alpha of 3 is 3, and alpha of 4 is 4. In other words, what you're plugging in is your input, what you're getting on the other side of the equal sign is the output. Let me set up another one and have you write it out. We'll call this one beta. So let's see here. This one, actually, hang on. Let's scooch all this stuff over if I can. There we go. Move. Let's move it over one line down as well. There we go. Okay. So we'll call this one alpha. We'll call this next one down here beta. And we're going to, again, start out with 1, 2, 3, and 4 on top. Always start out with them in the natural order on top. And then on the bottom, this time, I'm going to do it, let's see, 1 goes to 3, 2 goes to 1, 3 goes to 4, and at this point, pause it for a second. What do I have to make 4 go to? Well, I have to make 4 go to 2. Otherwise, it's not 1 to 1 and on 2. Okay, so now, what I want you to do here is find out beta of 1, beta of 2, beta of 3, a little bit more space, and beta of 4. Okay, don't worry, I'm gonna zoom out so you can look at it. Okay, so pause the video and find out what each of these things are. All right, if you're done, we find beta of 1 is 3. Oops. Beta of 2, we said in this case it was 1 again. Let me scooch that back a little bit. Beta of 3, we said was 4. And beta of 4 is whatever's left over, which is 2. And so, this is how we find it. So hopefully that makes sense to everybody. Now, I may not have to, well, we probably will have time to do all of the ones of a set of 3 elements, but let's go ahead and look at how does composition work. And this is nice because it, how does function composition, I'm abbreviating this, that's function composition work. How does function composition work? This is nice because it works exactly like it did for, if you'll recall, how we did D4, how we did the set of symmetries for a square. We have 2 of them together. We do the rightmost one first. Essentially, you're thinking about plugging something in, and essentially, if you're looking at alpha, beta, so we already know alpha, we know beta, so we want to figure out what alpha, beta is here. So I'm going to write them both out, and then we're going to talk about how you put them together. Okay, so 1, 2, 3, 4. Writing them out in order doesn't necessarily help, but I'm just going to do it so we have them all written together here. So that's alpha. This will be beta. Don't worry, I'll fill in the bottom rows too. 1, 2, 2, 3, 4. Okay, and alpha was 2, 1, 3, 4. And beta was 3, 1, 4, 2. And I'm actually going to do this sort of in 2 steps here. You don't have to do this in 2 steps, but I'm going to show you a way to do it in 2 steps. I don't think the book does this, but I think it might be helpful. And when I say 2 steps, I'm actually going to have an extra row on this thing that I set up. The second row is going to be sort of a dummy row. We're not going to need it in the end, but it will show you. That's so crooked. That's like the man with the crooked house or whatever. Okay, so the middle, that is not far enough down. Okay, so the middle row is going to be what happens first. The bottom row is going to be what happens after that. So what you want to think about doing here is this is a function. So alpha beta is equal to alpha of beta. In other words, alpha of beta of x, whatever x happens to be, sorry, alpha beta of x is equal to alpha of beta of x. And we'll do a full example of this for the first one. Okay, so for instance, alpha beta of 1 is equal to alpha of beta of 1. So we look back at our beta function and we see 1 goes to 3. So this means alpha of beta of 1 is alpha of 3. And then we look at what alpha does to 3. And alpha just takes 3 to itself. So we get 3 there. So let me show you how we can do this in our extra row thing here. So the first thing we do is the second one, is the right-hand one, because it's like plugging a function into another function. Like if you have f of g of x, you plug into g first, and then whatever you get out, you plug back into f. So remember here, let me move this down a little bit. One more. Okay. So remember, this here is alpha, and this here is beta. And unlike what we're used to in writing and everything, we do write first. So, because that's how we do functions. So, we go, our first row should be beta, our second row should be alpha. So 1, our first step goes to 3, because that's what beta does to 1. And then alpha leaves 3 alone, so that goes to 3 again. Okay, now, let me fix that a little bit. Okay, now what I would like for you all to do is pause the video and finish filling this in. So you can do the beta line first. There's really nothing to it, right? You just have to copy the second line of beta and then fill in the alpha line, which is a little bit more work because you have to rearrange things, but that's all you have to do. So go ahead and do that for me. And when you unpause the video, I'll show you what we should get. All right, if we're back, let's go ahead and fill in the beta line. It's 3142. We don't even have to do anything there. 3142. Easy enough. And I'll even put the arrows in here because I'm a nice guy. And nice guys draw arrows or something. I don't know. All right. Okay, so now for alpha, this is a little bit trickier. Not too tricky, but we'll see here. So alpha, we want to see what the things in the second line go to. So here we see 1 in alpha goes to 2, so I should have a 2 here. 4 in alpha goes to 4, so I should have a 4 here. And 2 in alpha goes to 1, so I should have a 1 here. So that is what we get. Now, like I said, this is not how we write our output. We write this just like a permutation, just like any of the others. So we write it in 2 rows. So 1, 2, 3, 4. But we can skip that middle row and just look at the bottom. So if we look here, we see 1 goes to 3. 2 goes to itself. 3 goes to 4. And 4 goes to 1. And this is what you get for alpha beta, right? So we had, over before, we had found what alpha was, or we'd said what alpha was, we'd said what beta was. This is alpha beta. So it is important to keep track of the order of these things. You do the right one first. Think about it like you're plugging in a function. Okay? So this is what we get for alpha beta, and you'll notice that it doesn't necessarily look that much like alpha or like beta, right? In fact, if we look at it here, 1 maps to 3 in alpha, beta, and beta. Nothing else. Oh no, also 3 maps to 4 in alpha, beta, and beta. But nothing else maps to the same things that they map to in either of the other ones. So it is different. It doesn't necessarily look like the same thing. Now, just another quick exercise. What I would like for you to do is find before I do that, let me put up another definition here. Definition. Okay. Now, okay. The symmetric group S, I'm going to leave a couple spaces here because I'm going to use something there, is the group of all permutations of the set one, I don't need space, 2, 3, up through N. Somebody's mowing outside, I guess. If you can hear that. If you can't, nobody's mowing. Alright, so here. Okay, the symmetric group, and here's where I need to put in a little S sub n. Hang on, let's make that 0.5. There we go. The symmetric group S sub n is the group of all permutations. So this is a little bit different from what we did before. This is all permutations. So every possible one from of the set 1 through n. So this is everything. So not just some, like we saw what we talked about with D3 and D4. There are some permutations that we don't get because we're talking about real-world rearrangements of a square or a triangle, and you can't change things certain ways. Like, you can flip a square over, you can rotate it, but there are things that you can't do. Like, you can't just swap the upper left-hand corner with the lower left-hand corner. There's no way to do that and keep your square whole. But this is all permutations. So what I would like us to do here real quick is to write these out. So, and not obviously for all Sn, but let's talk about S3. So S3 is the set of all, the group set. I'm going to call it a set here, but it is a group. And it's natural that it's a group because if we're talking about all permutations, you don't even have to worry about it being closed, right? because it's naturally going to be closed, because composing two permutation gives you another permutation. It's also a group of all permutations of the set, and that is a motorcycle. I hate that guy. He makes a whole bunch of noise all the time, but you know, what you gonna do? Alright, so you probably didn't even hear that. You probably think I'm crazy. Okay, so S3 is the set, and it's also a group of all permutations of the set 1, 2, 3. So what I would like for you all to do is write them all out. I'm going to barely have enough room here. That's why I didn't do S4, which you might imagine is the set of all permutations of 1, 2, 3, and 4. But go ahead and write out all of the possible permutation. Use this array notation that we're talking about here. Okay. So go ahead and pause the video and try and do that for me. All right, if you're back and you had trouble, first think about how many permutations there are. So let's start out with that question here. If you didn't have trouble, you know, you're just going to have to sit there a little while or fast forward, I guess. How many permutations are in S3? So remember, the elements of S3 are not 1, 2, and 3. They're permutations of 1, 2, and 3. Oops. Permutations of 1, 2, and 3. Okay. How many permutations? How would we figure that out? Okay, if you pause the video and you came back, here we have a quick answer. If we want to look at 1, 2, 3, we have to figure out how many options we have in each of these spots. A number of options in each spot. And what we find out is we have 3 options in the first spot, because it could be 1, 2, or 3. Once we pick one, we only have 2 options left, because remember, this is 1-to-1 and onto, so we can't reuse numbers. 2 options in the second spot. And finally, once we're done with that, we only have 1 option remaining in the last spot. In the third spot. So, what that tells us is S3 has an order of 3 times 2 times 1, which is just 6. So we have 6 elements in S3. Okay, and likewise, I know I'm sort of dodging what I originally asked you to do. But in Sn, we would find how many permutations? So how many permutations? And here the answer is very similar. You do the same kind of thing. And the order of Sn, you have n options for the first spot, n minus 1 for the next, and you multiply those all up and you get n factorial options. And there's a reason why this is. That's the number of permutations of that many elements. So, now, go ahead and pause the video if you didn't get them all written. Now you know how many there are. And I also, with this, sort of provided you a little guideline of how to do it. Okay, if you're back, here are all elements of S3. Let me try and write them out fairly quickly here. Fairly quickly here. We got 1, 2, 3. Well, the first one is just it maps to itself, and as you might expect, that will later on, when we get into this, turn out to be the identity. The next one, I'm going to leave 1 alone for now. And if I do that, the only other option I have there is to swap the 3 and the 2. And so those are the only ones that leave 1 alone. Now, the next option, 1 has to be replaced with something. So I'm going to replace 1 with 2. Well, there are 2 options for 2. One is it goes to 1, so we'll do that, and then 3 has to go to itself. The other option, if 1 goes to 2, is 2 can't go to 1, we've already used that. 2 would have to go to 3. And then 3, what's left? 1 has to go to 1. Am I about out of room? I am. Okay. And so, let's see, I'm going to have to finish up on the bottom row. This is going to make things pretty tight, but whatever. I can do it. All right, so here, 1, 2, 3. We've already looked at all the possibilities where 1 goes to itself and where 1 goes to 2. So the remaining ones have to have 1 go to 3. So 2 here can either stay the same, which I'll leave it there, and if that's the case, 3 has to go to 1, or I can have 1 go to 3 again, then 2 can't go to 3 because that's already been used, and we've already done one where 2 goes to itself, so 2 would have to go to 1, and then 3, at this point, the only thing left for it to map to is 2, and then these are all 6 elements of S3. That is the entirety of S3. Okay, and I think that pretty much covers that first section, hopefully anyway. So I will post this video shortly, and of course by the time you hear that, I will have already done that because, again, that is the way time works. It proceeds from past to future, never in the reverse. Alright, so hopefully this helps, and please let me know if you have any questions, and I will talk to you all later. Thank you. Bye.